This is ECE 341 Random Processes, Part 1, Lecture 10. Last time we began Chapter 3 and talked about discrete random variables. In this lecture, we're going to investigate what is called a family of random variables. A discrete random variable family is nothing more than a probability mass function with a particular form with adjustable parameters. These adjustable parameters allow us to customize a particular family of random variable to meet our particular situation. If you have a set of families to choose from, it's just a set of tools that allow us to quickly model commonly encountered situations. So we don't have to rederive models to match our particular cases. Not every family applies to every situation, obviously, and not every situation has a family to draw from. But these families are chosen because they are commonly encountered and therefore give us a really nice tool for trying to get through problems in an efficient way. We'll look at some commonly encountered discrete random variable families. Details of these and other families are found in the book in Appendix 8.1. So I really encourage you to take a look at that appendix and complete your knowledge of at least the most common families by scanning through those. Not every one that's in the appendix are ones that we will cover in class, but I'd still like you to look at each of those. So let's go ahead and start. We're going to start with a really simple example. We're going to look at what is called a Bernoulli random variable. So we'll go ahead and take our first example as being this one that is called a Bernoulli. So we have this idea of a Bernoulli random variable. This Bernoulli random variable is about as simple as it gets. It's an experiment which can result in either a success or a failure. So the experiment here, the experiment is a simple binary. It's a binary experiment, right? Binary experiment that results in either success or failure. I would make the comment that what we mean by success or what we mean by failure is dictated by the particular problem or situation we're looking at. Success sometimes might be a negative thing. So success might be contracting a disease, for example. You wouldn't want it, but from the context of the experiment, maybe that's the thing we're interested in modeling. So success here does not necessarily mean a positive thing. It just means an outcome that is successful, right? That you get something. Winning the lottery would be a success that is an advantageous one. Winning the lottery of a disease would be a success that is not so advantageous. So what does this binary or Bernoulli random variable look like? We would say something like this. I'd let the random variable x be equal 0 if it was a failure, something like that. And I'm going to go ahead and let x equaling 1 mean it's a success. So we know that this guy can only take on two states, and we would expect that there's a probability associated with each of these. So the probability, for example, that x equals 1, that's the success probability. We're going to go ahead and set it up equal to a parameter here. In this particular case, we're going to call that p. So the parameter for this family of random variables is p, and it just designates the success probability. That can be used because there's only two different states to help us understand what the failure probability is. The failure probability is going to be 1 minus p. No need to put in a new parameter in that case because p is enough to define both. So once we have those kind of basics for this one, it's a very simple experiment. We can come up with our probability mass function. And so this is the family of random variables that fall under this category of Bernoulli. Bernoulli random variables have a probability mass function that is equal to 1 minus p, right, when the outcome is 0, a failure, and it's equal to p when x is equal to 1, meaning a success. Will be complete in our definition. We'll say it's 0 otherwise, something along those lines. So we can go ahead and think of this as being our family of Bernoulli random variables. There is a constraint on this, right? So I'm going to put this underneath. A lot of times you might not include this if you were working with it. It's implied. It's the only way that you can get a valid probability mass function in this particular case. What is the assumption here? The assumption is that that probability p, right, is a valid probability, something between 0 and 1. It wouldn't really make a lot of sense, right, if you had little p equaling 10, for example, because a probability of 10 doesn't matter or doesn't make any sense. Same thing with a negative probability. So we are going to constrain the probability parameter p, right, to be a sensible probability. So I'll go ahead and mark that guy off. It's probably the simplest family model that we can come up with, and it just has two different states, success or probability. A lot of the things that we might do with discrete random variables can be based or working around this idea of success or failure. This Bernoulli model, for example, applies to a lot of situations that we've already seen. Flipping a coin, for example, is a Bernoulli experiment, right? You flip a coin and you have one of two outcomes come up. We would just have to decide which thing was considered a success. Maybe we're looking for whether we get a heads or not. If you're starting a football game, maybe heads coming up means that you get to choose the side or whether you do the kickoff. So you flip this thing, and head is considered success, a one. If it was a fair coin flip, that little parameter p would be zero point 0.5, right? A fair coin. So success and failure were each equally likely. So this Bernoulli is kind of the starting point for us. We can modify this Bernoulli to come up with another family, and so we're going to go ahead and try to do that now. So let's modify. Let's modify the Bernoulli model. Random variable. And the way we're going to modify it in this time is we're going to keep trying. So we're going to keep trying our experiment, keep trying. So keep trying whatever it is that we're doing. So we can say keep trying our experiment, this binary experiment. Our binary experiment, we're going to keep trying that until a success occurs. So there's lots of things that we would do in life where there's not a certainty in the outcome. You don't know if you're going to succeed or fail. And in the event you fail, well, then you just turn right around and you try again and you keep trying and you keep trying until you succeed. Maybe passing a class would fit into this. It's no guarantee that you're going to pass a class. If you don't pass it, you turn around and you re-enroll and you keep taking it until you pass. So how might we modify the Bernoulli, or how might we use a Bernoulli to help us come up with the probability mass function for this situation? I'm going to start out by looking at a tree diagram, right? And so if we're going to keep trying our experiment until we get a success, we still need a random variable on that. So I'm going to think about, let's count the number of tries. Count the number of tries. The number of tries. We're interested in how many times did it take before we got a success. So count the number of tries, right? Of tries until you get a success. And we will call that guy our random variable y, something along those lines. So y is already a random variable because counts are a number that fits on that real number line. There's no need to transform it any further than that. Our observations can be the random variable itself. I'm going to go ahead and draw a picture to help us kind of visualize this experiment. When I start out somewhere, so I'm going to start out here on the left, I have two possibilities because this is a Bernoulli trial, right? It can succeed or it can fail. I'm going to let the top branch here be the success path, right? It has a success and it has a success probability of p. And if I succeeded on the first trial, well, then what would I know? I would know that that random variable count was equal to 1. If I didn't succeed on that first trial, that would have been with probability 1 minus p, right? In which case I would be ready and trying to think about doing the experiment again. So I'd go and do another Bernoulli trial. And so that another Bernoulli trial would have a success probability p as well and a failure probability 1 minus p. If we happen to succeed on that, my count for the number of times it took me to get to a success would be 2. And it could keep doing that, at least in theory, forever. So the next one would have a p and a 1 minus p paths on there. If we happen to succeed on that third one, we'd get y equaling 3, and we can see the kind of pattern that's going on too. Okay, so this particular model can help us get that probability mass function that we're seeking for that random variable y. I will say that this guy's got a name. So this particular thing, this try until you succeed, is called a geometric random variable. So this model is what is called a geometric random variable. So this particular family, the geometric random variable, can be associated with a keep trying until you succeed kind of outcome. So what would the probability mass function look like? We know that probability mass function, py of y, right, is going to tell us the different probabilities for different values y that are in our range space. What is the range space? We can certainly see that coming up here on the top. The range space starts at 1. You have to try at least once if you're going to get a chance of having a success, right? And that could go on for a long time. time, especially if p was a very small value. So my range space here is going to start at 1 and go out to potentially infinity. So I'm going to need something like values of y equaling 1, 2, 3, going out forever, something along those lines. And what is the probability that y equals 1? Well, it would be p. What is the probability that y equals 2? It's 1 minus p times p. We would just multiply all the probabilities to get down that path. What's the probability that y equals 3? It's 1 minus p squared times p. There's always a p in there, right? And there's only one single p all by itself. That's when you got the success. And then you're going to have 1 minus p raised to, well, the number of trials minus 1, because it took that many trials before your last successful trial before you got it. So because we're just chaining these guys together, we multiply the probabilities together, and we end up getting something like this. We get a 1 minus p, right, to the y minus 1 times that guy times p. So there were y minus 1 failures before you got to the final, on the yth try, right, success, which had probability p. And this thing has a 0 otherwise. Something along those lines. If you take a look at the values of the probabilities, right, p is a value between 0 and 1, so is 1 minus p. Y is a non-negative integer, or it's a positive integer. And if we take a positive number raised to a positive integer, that's going to be positive as well. So we can certainly see in this case that all the probabilities are positive. They are non-negative. You could also use your basic knowledge of sums, and you could show that if you summed these sets of probabilities from 1 off to infinity, that the sum itself goes to 1, which is that accumulation to a final probability of 1. I won't do that here. That's in the book as well as online if you want to do that. It's also a pretty simple exercise. We'll do a few proofs of some of these a little later. So this is our second model that we've looked at, right? We started with the Bernoulli. That was a outcome of either a success or a failure. We've modified or used that Bernoulli to come up with our next model, which is a geometric, right? And that's the try until you finally succeed model. And now we're going to work on another modification that utilizes these ideas of Bernoulli trials. And this one is where we're going to count the number of successes out of a fixed number of trials. This certainly happens a lot. You might be in a manufacturing situation, as an example, and you produce 100 units of something over an interval of time, maybe over the production day, you get 100 units, and you want to know how many of those are passing all the quality control measures and ready for shipment, and those that did not pass all the quality control measures. So we can come up with models for this sort of situation as well, and that's going to lead to another family of random variables. So this next one that we're going to look at let's go ahead and test. Let's test n things, right? So go ahead and test n things. Think of them as products in a production line, right? Count the number of successes. Count the number of successes. And I'm going to call that guy X, right? And that total number of successes, right, is the total number of successes out of those n things. An example of this is that you might sit there and think of having a success, right, going on and doing that some x number of times. And if it came out of n things, what would that tell you? You would have some failures in there too. You'd have failure, all the way out, and failure. And how many failures would be there? Well, there would be n minus x, so that the total number of things that we are dealing with here are n. This shows a particular ordering of that. If I was going to think about the probability of that particular one, I have x successes, each with probability p. It's assumed that they all have equal probability in this model. And then there would be n minus x failures. So what would we get? We'd get p to the x, 1 minus p to the n minus x. But that's not the only way that we can have a total of x successes and n minus x failures. This goes back to some of our counting that we did in the past chapter. We know that we can have n choose x orderings of that. So if I want to come up with the probability mass function in this particular case, I have to allow for all those different orderings, and it leads to what is called a binomial random variable. So this particular guy is called the binomial random variable. It's basically a count of number of successes out of a fixed number of trials, that fixed number being n. And the probability mass function for this guy looks something like this. Px of x is equal to, right? Again, we're going to look at over being a range space. How many successes could we have when we're only testing n things? Well, there could be no successes, so x could be equal to 0. There could be 1, and it could go all the way up to n. You could have all of them succeed, especially if the little p value was quite large. That certainly could be a possible outcome. That's the range space, and I want to find out what the probabilities are for that. We know for x successes, there's a probability p to the x, and that has to be accompanied by the failures, that's 1 minus p, and there has to be n minus x of that because we were testing a fixed number n of objects. The only thing that we have to add on that is this count that allows for the different arrangements. We did that counting exercise in the last chapter, and that's going to be n choose x, something along those lines. And we would get 0 otherwise. Again, this is one of those ones that if you go through there, n choose x is always positive. P was a positive number between 0 and 1. X is just an integer, right? 1 minus p is positive. N minus x is also going to be an integer. You multiply all those together, they're always non-negative. So we can certainly see that this conforms to our requirement that the probabilities are not negative. If you sum this guy up, if you go on a sum from 0 to n of n choose x, p to the x, 1 minus p to the n minus x, you can show that that equals 1 as well. That is an exercise that we might look at later. I won't do it right now. I would just like to get these different families out. Let's go to the next one. So our next one is going to be combining, again, some of the stuff that we've worked on before. And so in this next particular one, oh, and by the way, I probably should have said this. I'm maybe being a little bit lazy here, but we know that this thing has requirements like 0 less than p less than 1, right? So that's still holding on these guys. We still expect that p, which is reflective of the success probability, is indeed an actual probability. So we have to keep those things intact. The next one I'm going to do is a combination of, again, some of the previous ones that we've looked at. So let's combine some previous. And the way I'm going to do that is I'm going to try to look at how many, you could think of this as the number needed to achieve a certain number of successes. So if I'm sitting there conducting a bunch of experiments over and over and over again, we did one, that was the exponential, where we kept going until we succeeded, right? So we kept going until we succeeded. That wasn't the exponential, it was the geometric. So the geometric was keep going until you succeed. This one's sort of a modification of that one. So we're going to be looking at keep going until you get k successes. So k could be more than 1 as an example. So I want to keep doing an experiment and so I can get a particular desired number of successful outcomes. Maybe I want to get 10, right? So I could have some experiment where I've got Bernoulli-like events where they can succeed or fail, and I want to keep going until I get a fixed number of successes. So in this particular one, I'm going to be looking at something like that. I'm going to look at the number needed, maybe the number of trials needed, the number needed, and we'll let that number again be designated by some variable x to get some fixed number of successes. Let's say call it k. So to get k successes, something along those lines. This has an assumption of independence. We've been assuming independence on a lot of this, so assuming independent trials. So we're going to go ahead and assume independent trials. If they weren't independent trials, things would get more complicated. We'll try to deal with more complicated later. But for right now, we'll just assume those independent trials. We know that that's going to allow us to multiply probabilities together. How do we begin to model this sort of thing? So if you think about something like this, a probability mass function does something like, what is the probability that x equals some value? So what's the probability that a random variable x takes on a particular value, little x? If we're looking for k successes, by the way, we know that little x has got to be at least equal to k. You can't get k successes if you use fewer than k trials. So the range space on this guy should probably start at k. If they all succeeded, once you got through k trials, you would have had the k successes if every single one of them succeeded. It could be that you had some failures in there. So one way of thinking about this is I could think about this as being the probability, right, that you have k minus 1 successes in x minus 1 trials. We've already looked at that kind of model. That was something we just did, and that we got success on the xth trial, right? So if I want to get a total of k successes, I'm going to keep going until I get the kth one. That means the very last one had to be a success. And in the x minus 1 before that, I had to have k minus 1 successes before it. So I've just split it up into two pieces, both of which I have models for, right? I know how to get a success on a particular trial, and I know how to get something like x minus 1 successes out of, no, try that again, k minus 1 successes out of x minus 1 trials. That was what we had looked at before for a binomial random variable. So if I go ahead and do that, I could do something along the lines of this. I'm going to call this first part up here, right? I'm going to call this first part up here something like A, and I might look at this guy down here, something like that, as being B, something along those lines. So let's deal with the probability of A first, right? Probability of A, right? That probability of A, so we're working on that red side of things. The probability of A is nothing more than what we had seen before for a binomial random variable, except for the total number of trials is not x, it's x minus 1, and the total number of successes is not a fixed number the fixed number here that we want for our successes is k minus 1. So number of trials, x minus 1, number of successes, k minus 1. And then I'm going to have p to the what? Well, how many successes? There were k minus 1. And then we have the failures, that's 1 minus p probability. And how many of those were there? There was x minus 1 minus the k minus 1, which we could clean up a little bit because the 1's cancel. You'll just get an x minus k on that particular one. What is the probability of B? Probability of B. B is easy, right? B is just saying that you had a success and you're on that single trial. So the probability of success there is just P. So that one's really easy. That blue line there is just going to be P. Now I combine the two together, and that's going to give me this model, right? Probability mass function Px of x, something along those lines. And this is what? X is counting, right? The number of trials necessary to get K successes. And the overall probability on this guy is going to be what then? It's just going to be a product of those two other ones. They were in sequence, and we just multiply them together. And so I'm going to get something like this. I'm going to get x minus 1, choose k minus 1. I'm going to have a p, right, to the k minus 1. And then I have, oh, but I multiplied that by p. So when I do that, I'm going to get just a p to the k, right? Because I take this p and I'm multiplying it into this guy. P to the 1 times p to the k minus 1 just gives me p to the k. No problem on that. And then I had a 1 minus p, and I can make this a little simpler by just making it x minus k. The 1's end up dropping out on that. This is on the range space. The trials have to at least equal the number of successes we were looking for. So this one starts at k and then just moves forward. It would be 0 otherwise, something along those lines. So we have this kind of modification of some of the stuff that we looked at before. If you go back through the families that we've discussed already, Bernoulli, right, that's just a success or failure. Geometric was keep going until you have your first success. Binomial was how do you get so many successes out of so many trials, right? And this one is doing something like how many do you have to go until you get k successes rather than just one success, but an arbitrary number k, something along those lines. So this guy also has a name, and so this is a random variable family as well. What are the parameters on this guy? Well, the parameters are something like what is the success probability? That's the p. But then the other parameter in there is k, right? The number of successes that we were looking for. This particular one is called a Pascal random variable. So this guy is called a Pascal random variable, right? And you could think of that with having parameters, with parameters little p in there, which has to be a valid probability, and a number of successes, k, right? And that number of successes is going to be an integer greater than or equal to 1, something along those lines. It wouldn't make much sense to talk about waiting for your 0th success. That just doesn't work. By the way, we can recognize, right, if we set k equaling to 1, what is that saying? It's saying how many trials does it take to get our first success? We've already seen that one, right? If k equals 1, right, what do we know? We know that the Pascal becomes, it goes to, right, this idea of a geometric. It goes in and it goes to that geometric random variable. So that geometric random variable is a special case of the Pascal, actually. It was probably easier to get that geometric first, and that's a really common one anyway, and so a lot of people just talk about the geometric, but it can be considered a special case of the Pascal. We can also look at one we'd already seen before. I'm going to do this for completeness. We've already seen it. There's also something called a discrete uniform random variable. This just means that they have equal probability over some range of values. I'm going to make it slightly more generic than what we had seen before. Previously, we had started at 0 and ended at some point to the right of 0. Let's do it this way. Let's look at a discrete random variable x, its probability mass function. It has to be some constant, and let's let the range of values that it takes that constant is going from some value k, right? Then you can go k plus 1, and you can keep going all that way out to some value L. And of course, there is an assumption here that K is going to be less than L, right? We would expect something like that. So we have a little block of values going from K to L that is going to have a constant. If you add the total number of elements there are in there, there's L minus K plus 1. So there's L minus K plus 1 total in here. If I look at this here, if I take a look at going from L or from K to L, there is L, right, minus K plus 1 slots or values here. So take, for example, K equaling 0 and L equaling 5. You go 0, 1, 2, 3, 4, 5. That's a total of 6 values. So 5 minus 0 is 5 plus 1 is 6. That equation seems to hold out. If they're all equally likely, the probability is just going to be 1 over the total number of slots that we have. So we're going to have a 1 over L minus K plus 1. If I have L minus K plus 1, each of which has a weight, 1 over L minus K plus 1, right? The total amount of probability in there is going to be equal to 1. Furthermore, if L is greater than K, then that probability is also non-negative, which is exactly what we need. And it's 0 otherwise. If I did a little sketch of this, this is very similar to what we had seen before. You're starting at some value K, you end at some value L, right? They all have the same values going through that, and it's 0 otherwise, and that value, right, is just given by 1 over the total number of points. In this case, 1 over L minus K plus 1, something like that. So pretty easy to see. We'd seen an example of this before. It just had the K term set equaling to 0. One more family of random variables I'd like to look, and then we'll do a few examples of showing these guys in action. Let's take a look at something called the Poisson random variable. So this last one that I'm going to deal with right now is called a Poisson random variable. It's not Poisson, it is Poisson. It's from a French name. So this Poisson random variable is really typical, or is really common in problems that involve things arriving. And so there's some parameters here, and we'll try to put it in terms of rates of arrival. So we are looking at a case where there is some rate of arrival. And this is one that I'll give an example a little later, and so we'll be able to see these parameters in action. There's going to be some rate of arrival parameter. So we're going to call that guy a rate of arrival lambda, and that's something right per unit time. So there's going to be some assumption of some unit time that our rate is taken over. So like so many people per hour, or so many photons per second, or whatever the case may be. And then we're going to have a time interval of interest. And that could change, right? So sometimes we might be interested in going over minutes or seconds or hours or whatever the case may be. And so we're going to let that time interval of interest be some t. And so that's obviously in whatever units of time that we're talking about there. Between these two, then, we can talk about something like, if we're interested in the number of arrivals and it follows a Poisson distribution, right? So we'll look at the number of arrivals. We'll be looking at counting the number of arrivals. So if, maybe we can do it this way. If the number of arrivals is Poisson distributed with, and the parameter for a Poisson is taken from a combination of that lambda and the t. So I'm going to say alpha equaling lambda times t. So lambda is a rate of arrival, right? T is the time value of interest. So the units on alpha are going to be just the total number of things, right? So if one was a number of things per unit time, and then you multiply it by time, then it's just the number of things. So alpha is like in the units of whatever things you're counting in here. If we have something that is Poisson distributed, and again, the book would maybe go through a little bit different level of derivation information on this guy. Its probability mass function looks something like this. This is one of the ones that is going to be one of the few that doesn't have that probability of success. This is not a Bernoulli kind of derived model. So Px of x is equal to what? In this particular case, it's an alpha to the x e to the minus alpha divided by x factorial. A little outside of our needs right now to derive where this came from. What's the range space? It's going to be 0, 1, going on out to infinity. You could have nothing arrive, or you could have one thing arrive, or two things arrive, or potentially a whole huge number arrive. The probabilities are necessarily going to get lower as we go along, and it's 0 otherwise, something along those lines. I do want to note, if we take a look at this alpha again, that alpha, lambda, right, is how many things arrive per unit time. That's a non-negative quantity. T is an interval of time. That's a non-negative quantity. You multiply both of those together, it is non-negative. So alpha is going to be greater than 0. So we're just going to keep that in mind. Because I just gave the probability mass function the family equation, I gave the equation for the probability mass function for a Poisson random variable. This one probably seems less intuitive. It's probably less clear that it actually is a valid probability mass function. So let's do a little of our proving that I didn't do for the other ones. Let's do a little bit of our proving on this one. So the first thing I would like to do is I'd like to look at, is Px of x, right? Is it always greater than or equal to 0? In other words, does this model ensure that the probabilities are always non-negative? Well, if we take a look at this, we have an alpha, right? That is greater than 0. We have x, which is greater than or equal to 0, right? Something along those lines. So we have two parameters. One is our random variable. One is the overall parameter for our Poisson, that alpha parameter. And the probability that we're saying equals to, right? We say Px of x is equal to alpha to the x. Okay, well, that is certainly greater than 0, right? E to the minus alpha. Alpha is a real number. E to the minus alpha, well, that's greater than 0. And we are, dividing that by x factorial. And ooh, that guy's greater than 0. So we can absolutely see that that whole thing is greater than 0. That's a check mark. So we know we are dealing with a model that will never return a negative value. The other thing we need to make sure is, do the sum of the probabilities over the range space of this random variable go to 1? So I would like to say, is it true that if we sum over all x an element of the range space of x and we add up the different probability mass function values, does it equal to 1? So we'll go ahead and try to do that as well in this case. I'm going to be summing now over x going on its range space. What was its range space? If you take a look up here and you look at the values of x, that it has this particular set of probabilities, it starts at 0 and goes out to infinity. So this is going to be a sum that starts at 0 and goes out to infinity. And what are we adding up? We're adding the probabilities, which we said are at alpha to the x, e to the minus alpha over x factorial. So in this particular case, I'm talking an alpha to the x, right? I have an e to the minus alpha over x factorial. And if I do that, I can go ahead and pull out the e to the minus alpha, because that is not a function of the sum variable x. So I can write this as an e, whoops, that's not an e. So I'm going to write this as a e to the minus alpha, and I have a summation x equaling 0 to infinity, right? And then I'm going to have what? I have alpha to the x over x factorial. Well, hopefully this is something that you recognize from calculus. So I hope you recognize this guy from calc as being equal to e to the alpha. If you take e to the alpha and you do something like a Taylor series on this guy, you do a Taylor or a Maclaurin, probably a Maclaurin is the one that's better. Maclaurin series are just a special case of Taylor, but we do a Taylor slash, oh my goodness, let's just get this a little neater. So Taylor, or a Maclaurin, right? Maclaurin series on that guy. If you do a series expansion, oftentimes this is how they define these particular guys. What is this guy equal to? It looks something like, if you look at this e to the something, the values that this guy is going to be is, it's going to be something like a 1 plus that alpha over 1 factorial plus alpha squared over 2 factorial plus alpha cubed over 3 factorial plus alpha to the 4 over 4 factorial plus, and so forth. If you take the derivative of this, it's equal to itself, which is exactly what the exponential is especially known for, right? It's equal to its own derivative. So that's just a series expansion of that guy. And if you compare that to what we had up there before, that is exactly what we see here. This is a summation of some alpha, whoops, that's going to be an alpha. That's equal to a summation of alpha raised to some power. Let's just do that power as x. Where does it start at? 0 to infinity, and I'm dividing by x factorial. So we see that that guy's an e to the alpha. If I go back then to my original here, if I look at this whole piece together, I get e to the minus alpha times e to the alpha, which does equal 1 as I expected. So you do need to go back and maybe look at a little bit of calc or maybe review your Taylor series if you wanted to do the full details in there. But that sum right there, a recognizable one. We've seen that guy before. So we have a probability model, right? If we look back at our probability model, that all these probabilities, right, they are greater than 0, that's great. And if I do a sum, right, if I do a sum of those probabilities, it does go to 1. So it does indeed meet our basic criteria for a valid model. And it's a valid model that fits this story of things arriving, right? This idea of having things randomly arriving and counting the number of arrivals over some period of time. Okay, so let's stop the development of these families for the time being and just do a few examples. I won't do an example for every single one of them. We've seen some examples before. I think some of them are self-obvious. Things like a Bernoulli trial, we already know. Something like a coin flip. We don't have to go through that again. Let's do a couple of examples taken from pretty simple situations and just see if we can, number one, identify the appropriate random variable family that applies to that situation, and then use that to compute some probability of interest, something along those lines. So let's think about the following. Let's think about the following example. We're going to have a fair coin. We're going to have a fair coin available that we can flip. So I hand you a fair coin, right? And you're allowed to flip it. And I would like to know a couple of probabilities. The first one I would like to know is I'd like to know the probability that 3 out of 5 of tosses are heads, for example, like that. What's the probability that if you went through and did 5 tosses, that 3 out of those 5 would become heads? So what's the probability that 3 out of 5 are heads? And the second one I'm going to look at is what's the probability that it takes 5 flips to get 3 heads. Now these seem on the surface similar, and they are similar, but they are not exactly the same. The first probability, if we take a look at A, right, what do we see out of that? We're looking for the probability that 3 out of 5 are heads. So the number of trials that we are doing here is fixed. The number of trials, right, the number of trials is fixed at 5, and we want to know, we want to know, right, what the probability that 3 out of that 5 are, let's call it successes, and that successes is just going to be our designation of heads, okay? Something along those lines. Well, if you go back through the families on there, we already looked at a case of counting the number of successes out of a fixed number of trials. That is a binomial model. So this thing reflects a binomial random variable. The model that is appropriate for this one is a binomial random variable. We've got a fixed number of trials and we're trying to count a certain number of successes. So if I use that binomial random variable's probability mass function, what am I going to do? I'm going to look at what's the probability, right, of x, that x equals 3, right? And you can think of that given n equals 5. So we're going to set that parameter, right? We had a parameter in the binomial distribution. N was one of them, right? Another one that was in it was the probability of success, p, because it's a fair coin. We know p equals 1/2, something like that. And we can go straight to the model and find out what the likelihood of that is. What does that equal to? Well, I had 5, choose 3, number of trials, choose the number of successes, right? My probability of success is 1/2. And the total number of successes we were looking for here was 3. And I'm going to have the failure probability, because it was a fair coin, that's the same thing. 1 minus a half is still a half. And I'm going to have 5 minus 3. If I do that, that is going to be 5 factorial over 3 factorial 2 factorial. And then I'm going to get a 1/2. Like bases, we just add the exponents. 3 plus 5 minus 3 is going to be a 1/2 to the 5th, something along those lines. If I go through all that work on there and I simplify it out, I end up getting 10/30 seconds, okay? Just a little bit under a third in this particular case. All right, so that's the first probability that we were interested in. What's the likely that 3 out of 5, right, are going to be that head when we're flipping a fair coin? 10/30 seconds. This was made simple, right? This is a relatively simple calculation, as long as I can identify an existing family, right, that applies to the situation. And it turned out one of our common models fit the situation nicely. So that really facilitated things. We didn't have to go through a new derivation of trying to find a probability model. We just used the model, and that's certainly preferred to having to come up with a model each and every time. Going back to the B one, what's the probability it takes 5 flips to get 3 heads? So this says what? This is more along the lines, if I think about it in a little bit different terms, if I'm going B here, we are going to keep flipping. We keep flipping, right? We keep flipping until we get some number of heads, right? We keep flipping until we get 3 heads. And then we're wondering, what's the probability that the number of flips needed, right, was 5. This is a slightly different situation, right? So we keep going, and what do we know different on this one? We know that the last flip, right, was going to have to be a head, right? So we were wondering, what is the probability that it took 5 to get those 3 heads? That's going to necessitate that the 5th one was a head, because that would be our end condition in this case. That's a little different than the one before, which could have had a fail on the last 5th. That would have fit the part A type one. It would not fit this part B one. If we think about this kind of wording here, we do see or recognize this guy as being a Pascal random variable. So this situation is reflective of a Pascal. We are going to keep flipping until we hit 3. So if you take a look at the Pascal random variable parameters, the K, right? So this is K equaling 3. I needed 3 flips on there. We still have that probability parameter, P equaling 1/2. And then X was just the total number of counts, and we were wondering, what is the probability that X was equal to 5? I can get that directly from the model, Px of little x equaling 5, using the Pascal model, right? And that guy looked a little bit different, right? It was what? It was this idea of x minus 1, choose k minus 1. So that is going to be, in this particular case, 4. So 5 minus 1 is 4. Choose 3 minus 1, 2. So I'm going to get 4, choose 2. And then I'm going to have my 1/2 to the 3rd, and I'm going to have my 1/2 to the 2 in there. So if you just go back up to the model, you can see all these pieces come out. A little bit different on that. If we go through and compute that out, that's a 4 factorial over 2 factorial, right? And a 1/2 to the 5th. So we still have that 1/2 to the 5th, but the thing that precedes it is a little different. Go through the math on that. We get 6/30 seconds, right? The first one we had was 10/30 seconds. This one is 6/30 seconds. So it's a little lower in probability than that part A one. One more example I'd like to do to finish the lecture out is I'd like to go ahead and do an example that's related to that Poisson distribution, just to show that guy operating as well. So let's get a story going with this one as well. So this particular example is going to have something like the following. Let's take a look at an emergency room. So we have an ER hospital room. So we're an ER hospital entrance, so an ER hospital. The ER hospital arrivals, let's allow them to be, and it's just going to be stated in this one, that the arrivals are Poisson distributed. So we're going to have someone else already have gone through the effort of determining that the arrivals followed a Poisson distribution. One of the reasons the Poisson distribution is a popular one, a named one that you find in basically every random book out there, is because a lot of situations where you have rate of arrival stuff naturally do follow Poisson. We're going to see some additional on this as well when we get to continuous random variables. We'll talk about something called the Gaussian or normal distribution. That naturally occurs out of just real world situations with a high degree of frequency. Many things naturally follow a normal distribution. Many rate of arrival type problems naturally follow a Poisson distribution. Not going to get too much in there. You can read a little bit more in the book, but let's just go ahead and take it as given that these ER hospital arrivals are Poisson distribution with, and we need some sort of rate of arrival. How could you get this? Well, you could just sit there and observe rate of arrivals at a hospital over a period of time and get an estimate based on what you physically saw. That's oftentimes what's done. So we have some lambda, and let's assume that people come in at about a rate of 15 per hour. So this particular hospital, this particular community, this particular situation is getting about 15 people coming seeking ER services per hour. I'm going to do a little bit more in here as well. We're going to go ahead and think about how these patients come in and what happens to them when they come in. So we're going to say the patients, right, are assessed. They are assessed on a first come, first serve basis. Well, no, we don't need first serve. We're just going to do a first come basis. A first come basis. So you get in line, and then they're going to try to figure out what's going on with you. So they're going to stay in a line just to figure out what the assessment is. So first come basis. And assessment, we're going to assume the assessment. We have to make some assumptions here. This is going to be perfect for every case, no, but we need a model, and so we're going to create a model. And the assessments are going to say take 5 minutes each. So let's let the assessment take 5 minutes each. As is the case in many models, you come up with parameters that are based on real world observations. They might not be true every single time, but the models themselves lead to useful information from which you can make decisions that affect things like the bottom line of your company. We'll see that as we go along. So a recap again, we have an ER hospital where patients are coming at a particular rate, 15 per hour, that happens to follow a Poisson distribution, which is not uncommon. Patients are assessed on a first come basis, and that assessment takes 5 minutes each, something along those lines. And let's go ahead and assume that assessments are done by one person. There's only one person up front, right? So that one person is the only person who is the gateway to the ER, something along those lines. I would like to know, what's the probability? What's the probability, right? Probability that a waiting line forms or occurs at the assessment phase. So in other words, if you're going to be coming up to the hospital, right, what's the chance that you're probably going to expect to have to wait in line before you're going to be addressed by this person to find out what's wrong with you? Everybody has seen these kind of situations, maybe not at a hospital, but you certainly see it when you go to the grocery store. You know that when you go to the grocery store, there are times when it's really busy and there's definitely longer lines. And we don't really like waiting in lines, and companies don't like their customers waiting in lines. That's generally not a good thing for a healthcare option like this. If you had super excessive long waiting times or a super high probability of having a wait occur, that definitely could be a liability or a thing that would result in poor outcomes for the patients. You also don't want to have too many people working, right? Because then you're wasting money having people sit at a desk when they're not likely to be used. So knowing what the probability of a wait occurring can help you make personnel decisions as to whether we need another person up front, something along those lines. So how can we make this computation? Because we already know the model that is this being used as a Poisson, right? We're going to just use that Poisson probability mass function that was already provided, and we just need to think about what does it mean to have a wait. So a wait occurs, right? A wait occurs if two or more patients arrive in the 5-minute assessment period. Assessment period. If nobody arrived, right, there's not going to be a wait line formed. If one person arrived over a 5-minute period, well, then no wait line occurred. But if 2 or more arrived over that 5-minute period, it's not going to allow everybody to get out of the line. There is going to be a wait occurred on that. So I want to be able to solve this with a Poisson. If you look back at what we had in there, we had an arrival rate in 15 per hour. But really, the time interval that is of importance to us on this is the 5 minutes, right? Because this idea of a wait occurring during the assessment time is 5 minutes. So we are going to use that period of interest, 5 minutes, right? And our rate of arrival, lambda equaling 15 per hour, to help us get the alpha, the parameter for the Poisson distribution, PMF, needed to make our probability calculation. So alpha in this particular case, right, is going to be equal to lambda t. What was our lambda? Our lambda was 15 per hour, right? What is our t? It's 5 minutes. That's 1/12 of an hour, right? Something like that. I shouldn't have the hour listing in the bottom. We should have it up in the top. 1/12 of an hour. The hours are going to cancel here, right? And we end up getting here a 15/12. So the alpha of relevance to us in this particular case is 15/12. So that tells me what? My px of x at least over for x an element of the range space x is equal to 15/12 raised to the x e to the minus 15/12 divided by x factorial. Probability of a wait, we already indicated what a wait event was. That was going to be when 2 or more show up, because the number of people who could show up could theoretically be many. It could be 2, 3, 4, 5, 6, all the way out to infinity according to this model. So we already see the model isn't going to be perfect. There's not infinite people on the planet, but these models work really well. The probability of any of those super high numbers is so small. Even though this model is not likely totally perfect, it's going to work very well for this case. I don't want to compute this by adding all those up. I just want to take the complement. So I'm going to do 1 minus what? 1 minus the probability that there were 0 in line or that there was only 1 in line. That's going to give me the probability of 2 or more showing up. This is only going to require me to evaluate 2 values, right? I'm going to take this piece of x and I'm going to use it to find this guy, and I'm going to use it to find this guy. If I did it with 2 or more and I didn't do it through a complementary, I would add P2, P3, P4 all the way out to P infinity. So it's just a decision here made for convenience of calculation. That's going to be a 1 minus. If you just go up to the equation up there and plug in 0 and 1, you get 0.35813 and you get 0.28650. So there's quite a bit higher probability for these low numbers coming in on this. And that whole thing comes out to being 0.355, something like that. So probability of a wait under this condition, right? If you have a hospital that's getting about 15 patients per hour, and that's Poisson distributed, and you have a single person working the front desk where it takes them 5 minutes to get through the assessment on these patients, about 35% of the time you would expect a wait to be forming. That's enough for this lecture. We'll pick up on what is called the cumulative distribution function in our next lecture.